Hello dear all, welcome back to Free Engineering School. Today we are going to discuss about the linear static analysis. Today's agenda is linear static analysis and Abaqus card, that is the input file for the linear static analysis we will discuss. Linear static analysis, as the name itself, the load is constant throughout the analysis in accordance with the Hooke's law within its elastic region. So there are some assumptions or conditions to be followed for linear static analysis. So as I mentioned, the relationship between the load and the deformation must be same, and rigidity and corresponding stiffness value for the material must be remain constant. Load applied is constant throughout the analysis. As you see in this graph, the whatever the loads you are applying, it should be constant till end of the analysis. Loads are assumed not to change the direction during the analysis. The direction should be same, which should not change with respect to time in during the analysis time. And the induced displacement must be very small, so it can be ignored, which is less than 2% can be acceptable during this analysis. So more than that it cannot be acceptable, like since we are applying a linear static material properties, it can be lesser than the 0.2%, and analysis must yield displacement very small enough so that we can ignore with respect to the stiffness of the material with respect to applied load. So in this slide, we are going to discuss in deep about Abaqus input file, which is commonly used for linear static analysis. Here I have divided into three nodes and elements, section and material properties, and contacts and steps. So in the nodes and element section, there will be a nodes and element category. We'll use a star node and followed by the number of elements. Each element, each node will have their coordinate system XYZ. And in the star element section, we have a star element property of element type C3D4, which I am just generically used, and with respect to the element set. So this is, suppose if you consider this as element set, so this element set is having a C3D4 element type in the under the category of star element. So these are the element numbers. So in the section and material properties, we will usually give sectional properties for a particular component or material. So this section, solid section, we can say here with respect to the element set provided by a 2D underscore plate, which will assigned with steel material properties. In the star material, we need to give a material property name and what are the material properties we are assigning. Here we are assigning only linear static properties, so I have given only Young's modulus and Poisson's ratio with respect to isotropic material properties. So in the contacts and steps, I don't have any contacts in this analysis. Just I mentioned in here as the one side it is fixed and on another side you have applied a unidirectional load. So I don't have any contacts or multiple components here. So contacts has been ignored. So I will take one more example on this study to understand how we can apply the contact properties as well. So in the step, as you can see clearly, there is a star step and followed by the name. I have given a linear static analysis. So this is the cards which are commonly used for static analysis. There is no manipulation here. This is the right straightforward card which has been used from the Abaqus. So in the star static, we need to apply uh, the sum of the initial time increment with respect to the total time and with respect to the minimum and maximum increments allowed. I will explain in detail here. So we need to understand how the displacement can be applied. So here I have a constraint in all directions, and here I applied in the y direction, if you say x and y. So under star boundary condition, we have given type displacement. So this is the constraint part. I have given all the directions constraint. I applied a load in the second direction. So load into second direction, I applied 1000 Newton, sorry. So this is the step, this is the initial part of the step, and this is the second part. So here I have extracted the results. Once I applied and given the boundary conditions, I need to extract the result to see how the model will behave. Under this, I have extracted the total force and what is the displacement it's coming out from this analysis, and stress and plastic strain, it is are not advisable. Just I put it here because in linear static analysis we are applying load within the elastic limit, so we will not observe any plastic deformations. So as I mentioned here, in the output result we will take a stress, displacement and reaction forces, etc. So coming to very interesting numbers here, I have mentioned 0.5, 1, 0.001 and 0.1. This is not a fixed one. You can adjust with respect to your analysis type, because it is purely depends on how we need to converge the model. So I will just explain what these numbers are. So 0.5 I have mentioned here is the initial time increment. Suppose if you are applying a 10 kilonewton load, so initial increment the 10 divided by 0.5 can be applied. So I will mention here, I will mention the initial time increment of 0.5, and 1 is the total time period for the given step, and 0.001 is the minimum time increment which can be allowed. Till this point the load can be applied, and this is the maximum time increment which can be allowed. So these are the points which are considered with respect to the type of analysis, and the analysis which you are using is whether with respect to complexity. With respect to the complexity, you can be interchanged. So this is purely on your basis. You can once use this criteria. If it is not converging, again you need to reduce the increment from 0.5 to 0.1 or 0.01, something like that. So this is all about the linear static analysis. You can take the note of it. If you have any doubts, kindly write to me in comment box, so we can discuss in offline as well as in the next coming videos. Thanks for now, and have a good day. Bye.